Okay, in the last part, I have shown you how we do the mathematical formulation of the inverse modeling, but actually it's not that simple. Let me show you why. Okay, so let's go back to the least squares for the straight line problem. So we want to find out the intercept and the slope, which are the two model parameters in here. We want to find them out. Okay, so this is like a general expression for the mathematical model for these two model parameter inverse problem. Okay, we have two columns here because we have two model parameters, right? And then we have big N in here, which is representing number of data and also number of equations we have in here. Okay, so we can change this into the expression looking like this, which is actually what we are doing in here. So D is the value in this y-axis, okay, and then 1 multiplied by m1, which is the intercept. It's not, the coefficient is 1, okay. We have the expression in here. And then C1, C2 is all these values are multiplying the slope in here, okay. So they are the values of x-axis, which is time in here, okay. In this problem, we have a very, very big issue in here because it's what we call overdetermined, because you cannot find one single line which is passing through all the dots in here. We have too much information in this case. There's no way you can find a line passing through all the points where the error equals to 0. Okay, so how do we define this overdetermined? We'll get to this later, but how do we define this? Is the number of equations number of n larger than the number of unknowns, the big M in here. So we define this as overdetermined. We'll get to this in the next section of this lecture. Okay. So how do we solve this problem? How do we find a straight line with the minimum error? Okay. So by error, we have a definition. So if we have a straight line, if we have found a straight line, then we have the value of d, which is predicted by your model. Okay, and then we have another d, which is from the observation. You have measured this. Okay, the blue dots are the measurement, and then the red line is the model. Okay, so we need to find the smallest overall error, big E. Okay, this is an individual E. The big E is actually the length of the E, okay, which is actually the square of the distance between the two values. We add them together, okay. This is, I think you have already learned this in your statistical course. We have just differentiate this over two model parameters in here. You can just do it analytically, and then we assume that it's 0 because we want to find the smallest E. We want to assume this is the smallest, so we assume 0. Okay, so for the overdetermined system of the equation, so this is how we find m1 and m2, because we have two equations and two unknown here, right? m1 and m2 are the two unknown. We have two equations, two unknown. So it's pretty easy to find them out for this straight line problem. But for the general linear inverse problem, so this is what we have talked about in the last slide. We have the model, we have the model parameters and data, and then we minimize the error to find all the m values, okay. And then in here, this is like a general linear inverse problem. How do we solve this if it's not just a straight line problem? Okay, if it's a general this is like a general solution. Okay, we multiply the whole equation by the inverse problem G, the inverse matrix, the transpose of this G matrix, sorry, the transpose of this G matrix, because we want to find out M, so we want to move everything over this side and then put M over this side. So G transpose dot G, we put these over this side, and this is the inverse of them. Okay, -1 is the inverse. So our job is to find out these. We have the matrix G, and then we have the data matrix or the data column, and then we calculate this. If we calculate this, we can find M in here. There is a mathematical proof for this, but I will not go through that because this is not a math course. So if you're interested, you can look at the link in here. Okay. So because this is the first time you are doing inverse modeling, so I have decided to give you a sample program. So these 2 pages are the one sample program. Okay, one sample Python program for doing this. So this is the graph that I've generated by this script. Okay, this is downloading the global mean estimates, the global temperature, the global air temperature, the global annual air temperature anomaly. Okay, we have talked about this example in the last section, which is yes, this one. Okay, I've downloaded the data and then I've done it myself. Okay, so we have different formulas for each of the data, which are the temperature anomalies. Okay, Z are the time in here, and then we want to find out the intercept and the slope. Okay, so we want to find out this, the linear trend, the intercept, and the slope. Okay, the data is actually the black dots in here. I have done some, the smoothing in here. It's not related to this problem. Okay, the red curve is not related to the problem. We just use the original data, which is the black curve, black dots in here, to calculate the trend. Okay, I'm sure you're more than capable to do this. So the major part that you need to be noticed is this part, is doing this general expression in here. So how do we find the model parameter? It's all about this. Okay, we need to do the dot product of G, transpose of G to G, and then the transpose of G to D. Okay, and then of course we need to do inverse of this. Okay, so please explore these functions in here, the Python functions. You can download the data, the CVS file in here, and then try the script to see if your Visual Studio is okay with this. Okay. So next we talk about the okay, so here is just for your reference how we do if we don't have a computer. How do we do the straight line problem by hand? Okay, if we have a straight line problem. So we have the expression of data equals to the matrix, the coefficients times the model parameters, and then we have the dot product of transpose of G and G in here. So this is the transpose of G and then G, and then we can if we have done the dot product for these 2 matrices, this is the result, and then so this is how we do the problem by hand. and then we have the estimated model parameters in here. This is just similar to the last slide, but it's for a parabola. It's a nonlinear model. The model is nonlinear because of this term. Okay, we can still do this. We don't need to rely on the statistical method in here because we have 3 model parameters. We don't want to do this 3 equations, 3 unknowns. We can just use the this method to solve the problem. Okay, so this is just another version of this. If the C square is another parameter, y in here, x and y, so we are filling a plane surface, so it doesn't matter what you are filling in here. You can use this exactly the same expression in here to find out the estimated model parameter. Okay, it's very convenient. So this is an example from the book. It's using the inverse theory to find the geological fault, to examine the earthquakes on geological fault.